Controlling a helicopter in flight requires moving the rotor blades. These blades, in addition to providing lift, are also control surfaces, much like ailerons, rudders, and elevators are control surfaces on an airplane. Moving these control surfaces would be easier if they weren't rotating, but they are rotating, so that's something we have to figure out. In this video, I'll show how blade motion for control of the helicopter is transmitted from the helicopter's stationary frame of reference to its rotating frame of reference. The key component we'll talk about is called the swash plate. The swash plate is an interesting device, so it's kind of cool to see how it works. To start the video, let's talk about the degrees of freedom of blade motion. I only want to talk about the mechanical transmission of control power, so I won't go into the aerodynamic reasons why these blade degrees of freedom exist. So the first degree of freedom is called blade feathering, sometimes also referred to as blade pitch change, and this is rotation of the blade about its longitudinal axis. The component that I have highlighted here is called the pitch change arm, and this is the mechanism that affects the blade pitch change. Pitch change can be all at once. This is called collective pitch change, or blade pitch can be once per cycle of rotation, and this is also called cyclic pitch change. And the interesting thing about feathering is that this is the only blade motion that's directly controlled by the pilot. The next two degrees of freedom are driven by aerodynamic and inertial responses to the movement of the helicopter. So blade lead lag is rotation about the blade's vertical axis, and the component that's highlighted in red here is called the lead lag hinge of the rotor head. Blade flapping is rotation of the blade about the rotor head's flapping axis, and the component highlighted in red now is the rotor head's flapping hinge. So in the video that you're seeing on the screen, all of the degrees of freedom that I've talked about are done by mechanical hinges. And the type of main rotor that uses mechanical hinges for these degrees of freedom is called a fully articulated rotor. A lot of modern helicopters have done away with mechanical hinges in favor of elastomeric components. These components bend and deform in response to blade motion. All three degrees of freedom still exist, but they happen by bending of virtual hinges rather than by the physical hinges that you see on the screen here. The tail rotor blades also move in response to pilot control inputs, but this is a much simpler control system as the tail rotor only needs collective pitch change. To move the control motion from the stationary frame of reference to the rotating frame of reference, there are two sets of controls connected via a swash plate. These are the non-rotating controls and the rotating controls. To show these, I'll hide everything except the mast, hub, and blades, and then I'll start connecting the two sets of flight controls in the video. So as we've already mentioned, blade feathering is controlled by the pitch change arms, and connected to these pitch change arms are these devices called pitch change links. These links are also adjustable, and mechanics use this adjustment to make sure that all of the blades fly in the same track. Tracked blades reduce vibration and improve the ride quality of the helicopter. A device called the rotating swash plate is connected to the bottom of the pitch change links. The rotating swash plate needs to have a drive mechanism to force it to rotate along with the mast and hub, and this mechanism is called the drive scissors. So these are all of the rotating controls. Before adding the non-rotating controls, let's see how the rotating controls respond to control inputs and blade motion. So here is collective pitch change and cyclic pitch change, lead lag, and finally flapping. And here are all of the degrees of freedom in motion at once with the rotor system turning. Remember, blade pitch is the only controlled degree of freedom. Lead lag and flapping are aerodynamic and inertial responses. Now we'll start showing the non-rotating controls. I'll hide the rotating controls first to make it easier to see. First, we need something to mount the non-rotating controls to, something that doesn't rotate, So we'll add a transmission adapter that'll be bolted to the top of the transmission. On this adapter, we add a spherical bearing that slides up and down. And around this spherical bearing, we mount the non-rotating swash plate. The non-rotating swash plate can tilt in the XY axis, and because it's attached to the sliding spherical bearing, it can also translate in the Z axis. The non-rotating swash plate would actually tend to rotate due to friction from the rotating swash plate, and there's normally a device called the stationary scissors that prevents that. I didn't animate it. Not exactly sure why. I guess I got lazy towards the end of building the 3D model here. Most helicopters control the motion of the non-rotating swash plate with hydraulic actuators, although some very small helicopters can move these controls with unboosted control rods with only the pilot's muscles as the actuation force. I ended my animated model at the hydraulic actuators, but in real life these would need an additional control connection that would take the hydraulic actuators down to the controls in the flight deck. This could be physical push-pull tubes that would attach to hydraulic pilot valves, or in the case of fly-by-wire helicopters, this connection could be a computer connection via electro-hydraulic valves. Those are all of the non-rotating controls, so all that's left to do is add back in the rotating controls. The rotating swash plate is connected to the non-rotating swash plate with bearings and grease. And these two swash plates pass control inputs from the stationary frame of reference to the rotating frame of reference. And this is how helicopters are controlled in flight. Well, now we're done building our helicopter control system. Let's go ahead and just do a final actuation of all the controls here. So with the helicopter blades stationary, this is collective pitch, longitudinal cyclic pitch, lateral cyclic pitch, lead lag, and flapping. Now we'll start the rotor system rotating, and once again, collective pitch, longitudinal cyclic pitch, lateral cyclic pitch, lead lag, and flapping. I'll point out too that I'm doing these degrees of freedom one at a time, but in actual nature of a helicopter flying in the air, it's not going to work that way. The pilot will put in control inputs to make the blades feather, and in response to this, they're going to flap and lead lag as they move around the azimuth of rotation. I'm also aware that there's a whole bunch of experienced helicopter people right now that are looking at the swash plate tilt for lateral and longitudinal cyclic, and they're thinking that it's not animated correctly. I did a separate video on this on the concept called phase lag for helicopter control input. It's an interesting topic. If you think that I've got it animated incorrectly here, I would encourage you to watch that other video on helicopter control phase delay. The link to that video is in the description. This video was just a very brief introduction to helicopter rotor control. We talked about blade degrees of freedom, and we talked about how control power is transmitted from the non-rotating frame of reference to the rotating frame of reference. These short topics barely scratch the surface of everything that's involved in controlling a helicopter in forward flight. Helicopters are a fantastic lesson in complexity, where things that look simple from a distance get more and more complicated as you start peeling back the layers and looking deeper into how the thing works. There's so much more to learn about helicopter control, and I hope this brief look that we did in this video motivates a few of you to look a little bit deeper into the topic. If you enjoy this content and want to see more, please like, subscribe, and leave comments about what you'd like to see next. Thank you for watching.